Swayam Prabha. Digital India. Educated India.
And with the next presentation, the last presentation is in person, and it's from Kyoto University. It's going to be presented by Ayumu Nabitani, and it's from Prof. Kano's group. They're going to talk about set point determination method for control of pharmaceutical critical material attributes in two consecutive processes.
Thank you, Chairperson. Now I'll start my presentation. In the pharmaceutical industry, continuous manufacturing has been attracting attention in recent years as a means of reducing costs and improving the quality of the final product. Examples of applications for pharmaceutical continuous manufacturing include solid dosage for manufacturing processes, which consist of granulation, mixing, and tableting. In the pharmaceutical continuous manufacturing, the ICH Q10 document requires establishment and maintenance of a state of control, which is defined as a state that consistently provides assurance of the continued process performance and product quality. To meet this requirement, the quality by design QBD approach, which aims at designing processes that can reliably guarantee quality instead of testing quality, is suitable. There are two factors that affect the critical quality attributes CQAs for pharmaceutical products: process parameters PPs and material attributes MAs of raw materials and intermediate products. An example of PP is a screw speed in a granulation process. An example of MA is the particle size of intermediate products after granulation. Among these, PPs and MAs that have a significant impact on CQ variation, this should be controlled to assure quality, are called critical PPs, CPPs, and critical MAs, CMAs, respectively. The quality by design approach, QBD approach, assures quality by keeping CPPs or CMAs within an area called design space, DS. This study focuses on how the CMAs are kept within the DS. Here, I will explain the existing problems when keeping CMAs in the DS. In this case, we consider the case. In this study, we consider a case where two distinct processes are taken from a production line, and one CMA is supervised from each process. The outer blue rectangle is an area indicated as assuring the required quality, and it is called the YDS. Traditionally, as shown in the left rectangle, a DS with independent upper and lower limits for each variable has been used in the pharmaceutical industry for ease of use by operators in the factory. We call this a conservative DS. When a conservative DS is used, some products may be discarded because they are just as not satisfying the required quality, even though they actually meet the required quality, as shown by the blue dots in the figure. Such a rate can be reduced by using a YDS as it is. However, when using a YDS, the CMAs may be affected by disturbances and may vary, so it is necessary to control the CMAs to keep them within the DS. And an appropriate control method is required to utilize the YDS to the fullest. This study proposes a method to appropriately determine the set point of CMA2 in the downstream process, according to the variation of CMA1 in the upstream process. The proposed set point determination method was tested in a control simulation using the process shown in the figure to verify the performance of the proposed method. The thick arrows represent the flow of material, and the thin arrows represent the flow of information. EAT measures the CMAs of continuously flowing intermediate products in real time. The CMA1 measured by the PAT is given to the set point calculator, which calculates the set point of CMA2 and controls to process 2 using a single PP. This slide shows you an overview of the proposed set point determination method. The proposed method consists of two major steps. The first step is to predict the CMA1 value at exit of process 2, CMA12, based on the CMA1 value measured at upstream exit up to the current time, CMA11. The second step is to determine the set point on DS based on CMA12 at time t plus theta. Theta represents the minimum time for material fed into process 2 to pass through process 2. Since this method determines the set point by predicting CMA1 at the exit of process 2 at a future time based on the residence time distribution, we named this method the proactive residence time distribution-based method, abbreviated as the PRTD method. Next, you see the residence time distribution, RTD, used in the PRTD method. When considering RTD in pharmaceutical continuous manufacturing, as shown in the figure on the left, a model combining a single PFR model and NCSR models is often used. The RTD functions are expressed, shown in the upper right figure, and the equation is shown below. M is the mass flow rate at process inlet and outlet, and MTKT is the mass of material fed into process 2 at fed into process at time tk, that is removed from process at time t. The RTD functions is monotonically decreasing when n equals 1, and convex upward when n is 2 or more. This slide explains how to calculate the CMA1 at exit of process 2. Let YTK be the CMA11 of the material fed into process 2 at time tk. By using this, we obtain the CMA1 at the outlet of process 2 at time t, CMA1 to t. The figures show the CMA11 for material fed into process 2 at different times, and the RTD functions for those materials. The RTD functions are for n equals 4. It's corresponding to a CMA1 of the same color. We consider that material removed from process 2 at time t contains material fed into process 2 at different times, and that the CMA12 for this material is calculated as a linear sum of these materials. In the equation below, YTK is weighted by the mass MTKT. The CMA11 for material fed into process 2 at each time t are added together to account for the mixing. In this case, we assume that the effect of material with small mass released from the process on CMA12 value is small enough, and limit the range of addition by T0 and T1. Due to time constraint, I will not go into more details. This equation exploits the time zeta between when a material is fed into process and when it begins to leave it, allowing a calculation of values up to a time of theta seconds ahead. The proposed method uses the value at the time of theta seconds ahead. Next, I will explain how to determine the set point on DS. When CMA1 is CMA12 when CMA1 is CMA12 at time t plus theta, CMA2 high and CMA2 low are the upper and lower limits values of CMA2 on the DS. CMA2 set t represents the set point of CMA2 at time t. In this study, CMA2 set t is the average of the upper and lower limits values of CMA2, so that CMA12 and CMA22 are less likely to be outside the DS. Next, I will explain the set point determination method used as a compared method. We use three methods. The first is the fixed SP method. This is a method of fixing the set point. Second is the MRT method. This method determines the set point based on mean residence time, MRT. At the current time t, the material removed from process is considered to be the material fed into process at the time that is mean residence time earlier. And CMA11 at the time that is mean residence time TM earlier is used to determine the set point. Third is the RTD method. This method uses the value at the current time. This is based on the RTD function and determine the set point. The proposed method uses a value at the time of theta seconds ahead. This method uses a value at the current time. I will explain the simulation we performed to evaluate the performance of the proposed method. First, CMA2 is influenced by CMA1 and the process parameter, PP. The transfer function shown in the figure was used as a transfer function to CMA2. CMA1 varies and is a disturbance to CMA2. From this transfer function, CMA2 and CMA1 are negatively correlated. In this transfer function, T represents a time constant, and three different values of 1, 10, and 100 were used in the simulation. Next, let's look at the RTD function of process 2. The equation shown at the bottom is the RTD function for material fed into process 2 as time tk. The parameter tau is assumed to have the same value as time constant t, and three values of 1, 10, and 100 were used in the simulation. I will explain the PI controller used in the simulation. In this study, the CMA of the downstream process is controlled according to the variation of upstream CMA. In this simulation, process 2 is controlled by a PI controller with PP as the operating variable, and the CMA2 as a controlled variable. The controller parameters proportional gain Kp and integration time Ti were determined using the SIMC method. Next, you see the DS used in the simulation. We evaluated ability to maintain both CMA1 and CMA2 in DS at the exit of process 2. To evaluate whether the CMAs could be maintained by controlling the downstream CMA in response to variation of upstream CMA, CMA1 was generated to vary in a range of 20 to 62, which is expected to keep CMAs within DS. We ran the simulations for a total of 4,000 seconds, and the first 1,000 seconds were excluded from the result to remove the influence of the initial values. This slide shows the result. The table shows the duration that CMA12 and CMA22 have been out of DS. We call this T out. For each style, we can see that the PRTD method has the shortest T out. In particular, it can be seen that the T out is 0 for RTD and PRTD method as T equals 100, but only for the PRTD method as T equals 10. We also see that T out becomes shorter as tau increases, except for the MRTD method as T equals 100. These reasons are discussed next. First, we consider the reason why the T out is 0 for PRTD method at T equals 10. This is a comparison of CMA2 between RTD and PRTD methods at T equals 10. This figure shows the path of CMA2 change abruptly, e.g. around 1800 seconds. The path denoted by a red circle shows a variation such that CMA2 decreases and then increases abruptly, indicating a horn-like shape. This is because this time CMA1 and CMA2 are negatively correlated. So when CMA1 increases, a disturbance is added that decreases CMA2. It can be seen that a disturbance such as a horn-like shape is smaller in the right figure than in the left figure. This suggests that PRTD method suppresses the effect of disturbances better than other methods and keeps CMAs within the DS. Next, we consider why the T-out becomes shorter as tau increases. The figure shows the disturbance applied to CMA2 by CMA1. The black line represents tau equals 1, and the red line represents tau equals 10, and the blue line represents tau equals 100. It can be seen that the disturbance fluctuates more slowly as tau increases. This suggests that for all methods, disturbance fluctuates slowly as tau increases, and making it easier to follow the CMA2 to the set point and keep CMAs within the DS. Finally, let us consider why the T-out when tau equals 100 using MRT was longer than when tau equals 1 and when tau equals 10. This figure shows the CMA12 as tau equals 100 and the CMA11 at a time that is mean residence time area used to determine the set point by MRT. It can be seen that the difference between two is large. Therefore, when tau equals 100, if the MRT method is used to determine the set point cannot follow the actual CMA12 variation close enough. This is so to increase the time of deviation from DS. I'd like to summarize the points of my presentation and give a glimpse into a future work. We propose a method to predict the CMA1 at the downstream process outlet at a future time based on residence time distribution from CMA1 in the upstream process, and to determine the set point, determine the CMA2 set point on DS based on CMA12 at time t plus 0. Control simulation results show that proposed method, proactive RTD method, is the best in terms of keeping CMAs within DS. In the future, we'd like to expand the method to deal with cases where there are more than 2 CMAs and more than 2 processes. With that being said, I'd like to wind up my presentation. Thank you very much for your attention.
Thank you very much. So we have time for maybe one question. Yes, Nikesh?
Okay, I'll start off by asking you the question that, since the presentation is based on the premise that a lot of attention is in pharma is towards continuous manufacturing now, and when you do things like feedback control, etc. Right? So the first question is, what do you do with sampling time when you are identifying, let's say, time series model or any IIT model for that matter? How do you determine the sampling time in a pharmaceutical setup for processes that are conventionally batched? So for continuous, when it becomes continuous, are there any thumb rules? That's my first question. And I have a couple of questions about these slides as well. On slide 13, we talk about the duration for which a given process goes out of the bounds. What about the magnitude? Does that matter as well? Is it just the duration? And lastly, you spoke about different time constants for disturbances, and it's pretty obvious that if you have slower disturbances, they're easier to reject. That you show, right? If you are time constant of 100, for instance, it's easier to just reject. So I'd like to know what are the usual time constants for the disturbances that you would envisage in a pharmaceutical setup? Thank you.
Okay, thank you. First question is about semi-continuous, but include the batch process. The case, yeah. Oh, okay, yeah. Yeah, that's a good question. Yeah, so if the production line includes batch process, we expand the method to deal with case in such a case. And in now I can't the solution to as was the case. So yeah, but in the future we would like to expand method to these cases. And second question is about defined time constant. In such case, we should simulate. We should learn simulations in such a case. But in such a case, I consider the proposed method is the best in such a case. So in the future, certainly I would like to run the simulation in such a case, but I consider the productive time distribution based method is the best in such a case.
Thank you very much. This concludes our session. I would like to thank all the speakers and also audience for participation. Thank you very much. I think we have a 20-minute break and then we have the next session. Thank you.